Everyone, welcome to the chemistry channel. So today we're going to be discussing a very important lecture, and this lecture is going to be focusing on limiting reactants. So in this video we're going to be talking about 4 different topics, the first of which is chemical equations, the second of which is yield, the third is limiting reactants, and then lastly a practice question. So with that, let's begin. Now I already wrote some stuff here just to decrease the length of this video, but we're going to go over it together. So remember that we talked a lot about chemical equations, and chemical equations are used to represent a particular chemical reaction. And oftentimes in a chemical equation you'll see these coefficients next to the different reactants and products. And these number coefficients correspond to the number of moles of each molecular compound that is required to complete the reaction. So for example, in this reaction here, you have 2 moles of H2 reacts with 1 mole of oxygen gas to form 2 moles of H2O. So these different numbers in front of the different molecules and compounds here represent the number of moles of each molecule or compound. Therefore, we can use these chemical equations to predict the amount of product we can get from a reaction. And this amount of product that we can get is the yield. So the yield is basically how much product is made from the reaction. So we can actually use the coefficients in the chemical equation to basically predict how the reactants are going to interact with each other and in what proportions in order to predict the amount of product made. So these chemical equations are very powerful, and that's what we're going to be doing today in our limiting reactant video. So since we introduced the topic of yield, which is basically how much product is made in the reaction, we can now start talking about a specific type of yield. And this specific type of yield is called the theoretical yield. The theoretical yield is the calculated yield of the reaction. So it's basically the predicted yield. You use math and stoichiometry and proportions in order to predict the amount of product that you are going to get. And however, the theoretical yield has an assumption. It assumes that all limiting reactant, so from now on I'll symbolize limiting reactant as LR, has been used. So theoretical yield assumes that all of the limiting reactant has been used. None of it is left over. Now, this is not the case in real life. Oftentimes you'll have unreacted materials, and that's when we're going to get into percent yield. However, before we get into percent yield, I think it's very important to talk about the limiting reactant. So what is the limiting reactant? Well, the textbook definition of limiting reactant is the reactant that is completely used up in the reaction. So it's the reactant that is completely used up in the reaction. Now, in order to understand limiting reactants, I have a little analogy here. So it's a little fun analogy. So imagine you have a chocolate ice cream cone, right? So you have this chocolate ice cream cone. And this chocolate ice cream cone, in order to make it, requires one cone. It requires 1 cone and 1 scoop of ice cream. So this particular ice cream cone requires you to have 1 cone and 1 scoop. However, what if you have 9 scoops of ice cream and only 6 cones? How many ice cream cones could you make? Well, the amount of ice cream cones that you could make determines on whichever thing that you have less of. In this case, you have less cones than ice cream. So therefore, it's the amount of cones that determine the amount of ice cream cones that you make. So you can't make 9 ice cream cones, you can only make 6 ice cream cones. So that's basically the idea of limiting reactants. In this case, the cones are the limiting reactants. And therefore, limiting reactants are what determine the overall yield of a reaction. So limiting reactants are what determine the overall yield of a reaction. And this same idea with the ice cream cones can be applied to chemistry as well. So let's see how we can apply this to chemistry. Believe it or not, there is one way that you can very easily identify the limiting reactant in an equation, and that is through reaction units. So the limiting reactant is the reactant that has the smallest number of reaction units. So what is a reaction unit? Well, reaction units are actually very easy to understand. So reaction unit. So a reaction unit is actually just a ratio. So a reaction unit is equal to the moles of reactant present over the moles of reactant in the chemical equation. And that is the reaction unit. So you basically divide the amount of moles, you divide the moles of reactant in the chemical equation of that particular reactant from the moles of reactant that you have. So in order to show how this works, let's do a very simple example. So let's bring up our classic equation that we usually use. So this is our example equation. So imagine that we have 8 moles of H2 and 6 moles of oxygen gas. So what is the limiting reactant? Well, this is actually very easy to find out. All you have to do is find the amount of reaction units for each of these species here. So let's do H2 first. So the reaction units of H2. The reaction units of H2 are equal to the amount of H2 that you have. So we have 8 moles of H2 over the amount of H2 in the chemical equation. In this case, we have 2 moles of H2. And when we divide these from each other, you get 4 reaction units of H2. So now let's do the same thing for O2. So reaction units of O2 is equal to the amount of moles of O2 that you have, so 6 moles of O2 over the amount of moles in the chemical equation, which is just 1. So 1 mole of O2. And when you divide these from each other, you get 6 reaction units of O2. Now, the limiting reactant is the species that has the lowest number of reaction units. So in this case, H2 is the limiting reactant. And that's because H2 has 4 reaction units, while O2 has 6 reaction units. So that's actually, this method is a very good way in order to determine which species is the limiting reactant. And that's half the battle for these types of problems that you're going to get in general chemistry. So we got to talk about one more topic before we get into the practice question. So this last little topic is percent yield. So percent yield. And percent yield is an expression that relates theoretical yield to the actual yield. So what is the actual yield? So the actual yield is the amount you actually get in a reaction. So the amount of product you actually get in the reaction. So it's after you complete the experiment, you measure the amount of product you get, and then you can compare that amount to the theoretical yield. And the equation that you can use to find percent yield is this. So it is equal to the actual yield over the theoretical yield times 100%. So that is the equation that you can use in order to find the percent yield of your reaction. Okay, so now that we have a pretty good idea of how to find limiting reactants, percent yield, theoretical yield, and an idea of what limiting reactants are, we can now put all these ideas into practice by doing a practice question. Now, all of the limiting reactant practice questions can be solved in pretty much the same way. So the best way to practice for these types of problems are to do some practice questions in the end of your textbook or practice whatever your professor gives you. So with that, I'll show you how to do one type of practice question for limiting reactants. So imagine, you've seen this reaction before in some of my earlier videos. So imagine you have CH4 reacting with 2O2 going to CO2 and 2H2O. So the first step in every single limiting reactant problem is to balance the chemical equation. Now, I already balanced this equation for you, so you don't have to do that, but you should always make sure that the chemical equation is balanced before you do anything with it. Otherwise, you're going to get wrong answers. And if you're having trouble with balancing equations, I have a whole video dedicated to that, where I just talk about the methods of how to balance equations. And we actually balance this equation in that video as well. So if you're having trouble with that, please go look at that as well. So since this is already balanced, we can sort of skip this first step here. So my question is, what is the theoretical yield of CO2 if you have 6.00 grams of methane and 18.00 grams of O2 gas. And I want your amount in moles. So I'll make it a little easier on you so you don't have to convert it to grams. So this is the values I want you to use for the molar masses. So carbon, let's just say, is equal to 12.01 grams per mole. Oxygen is equal to 16.00 grams per mole. And hydrogen is equal to 1.01 grams per mole. So these are the values I want you to use. So I encourage you, if you want to pause the video and try it for yourself if you already have a good idea of how to do this. However, if you don't, I am going to go over it right now. Okay, so the second step in order to solve these types of problems is to convert grams to moles. So we have to convert the grams to moles. Okay, so let's start off with methane. So we started off with 6.00 grams of methane. Now, in order to convert this to moles, all you have to do is multiply this value by the inverse of methane's molar mass, which is 16.05 grams per 1 mole of methane. Now, if you don't know how to measure the molar mass of something or calculate the molar mass of something, what I want you to do is to go back into one of my previous videos, I think where I first introduce empirical and molecular formula, where I discuss a lot about how to calculate the molar mass of something. So what we do is we multiply by the inverse of this molar mass here, and the grams cancels out, giving you moles of methane. And when you plug this in your calculator, you should get something around 0.3738. Now I'm going to put a little underline here in order to indicate the amount of sig figs that you should have, because we have 3 here and 4 here, and since you keep the same amount of sig figs as the value with the lowest number of sig figs, we have 3. And this is 0.3738 moles of methane. So that's our first value. So now what we're going to do is we're going to find out the amount of moles of carbon. So we do the same thing. So 18.00 grams of O2, and the molar mass of O2 is 32.00 grams per 1 mole of O2. And then when you plug this in your calculator, grams cancels out, and conserving the same amount of sig figs, you get 0.5625 moles of O2. Okay, so then we can move on to the third step in order to solve this type of problem. So the third step is to convert moles into reaction units. So this is the part where we have to determine the limiting reactant. So this is the most important part of this process. So let's do methane first. So we had 0.3738 moles of methane, and in the chemical equation, if you look back at it, you'll see that it requires 1 mole of methane. So this gives us the reaction unit, which is pretty easy, you don't even need a calculator, of 0.3738. So I'm just going to put the little underline there for sig figs. Reaction units. So that is for methane. Now let's do the same thing for oxygen. So we have 0.5625 moles of oxygen over 2 moles of oxygen. That's from the chemical equation that we have above. And when you plug this in your calculator, you get 0.2812, so put a little underline there, 5 reaction units of oxygen. So here we can make the judgment now. So the species with the lowest amount of reaction units is the limiting reactant. So in this case, O2 is the limiting reactant. So now we can actually figure out the theoretical yield of this equation, of this problem. So now we can actually do, so this is step 4. So find the theoretical yield. So this is the last step. So I'm just going to change my color here. So let's do this green. Okay. So since oxygen is the limiting reactant, it's oxygen that's going to determine the yield of our reaction. So let's take the amount of moles of oxygen that we had, which is 0.5625 moles of oxygen, and then you multiply that by the conversion factor. And in this case, you multiply this by 1 mole of CO2 for every 2 moles of O2. And that comes directly from our chemical equation, because if we look back at it, for every 2 moles of oxygen gas, you get 1 mole of CO2. So the moles cancel out, moles of O2 cancels out, and when you plug this in your calculator, you get 0.2813 moles of CO2. Now just a little add-on here. So this is just a little bit of an add-on. So let's say that our actual yield, so this means actual yield, was 0.1893 moles of CO2. What is the percent yield? Now this is very easy. Remember that percent yield is equal to actual yield over theoretical yield. This means theoretical yield times 100%. So all you have to do is take this actual yield, so 0.1893 moles, over the theoretical yield, which was 0.2813 moles, times 100%. And then when you plug this in your calculator, so I'm doing it right now. You get, now conserving the same amount of sig figs, so 67.29% yield. So that is it. That's how you solve pretty much many of the different limiting reactant problems. You basically, the main battle is to find the limiting reactant, to identify that limiting reactant, and you can do that through reaction units. And the other key to solving these problems is to make sure that your chemical equation is balanced, because you will not be able to solve these problems correctly without a balanced chemical equation. So remember, the main 2 things are to balance that chemical equation and to find the reaction units. The rest is pretty easy from there. So that is how you do limiting reactant problems. So with that, guys, I thank you, and I hope to see you next time. See you around, guys.